Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Vorhies, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking Pivotal for sponsoring today's event. Pivotal is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Tableau, Microsoft, Hortonworks, Oracle, IBM, and Teradata, to name just a few. Past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide very useful insight into a wide variety of topics of interest to our data science community. Today's webinar is entitled Data Science-Driven Approaches to Malware Detection. And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be 1 hour long. We'll have one panelist that I'll introduce in just a minute. There'll be a 10 to 15 minute QA following the presentation. And this event is being recorded and will be available on datasciencecentral.com in the next few days following today's presentation. I'd also like to encourage the attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the QA portion of today's event. So I'm very pleased to introduce today's speaker, Anirudh Kondaveeti, Ph.D. and Principal Data Scientist with Pivotal. Anirudh's focus at Pivotal is on security data science and spatiotemporal data mining. He's developed statistical models and machine learning algorithms to detect insider and external threats, as well as needle-in-a-haystack anomalies in machine-generated network data for leading industries. He's also an active collaborator with universities to advance spatiotemporal data science research and to develop machine learning tools in open source platforms. Prior to joining Pivotal, he received his Bachelor of Technology in Material Science from IIT Madras and his Ph.D. in Industrial Engineering from Arizona State University. Thanks for being with us today, Anirudh. We're looking forward to your presentation. The malware detection with enterprise networks is a critical component of an effective information security strategy. A watering hole attack is one example of how legitimate websites can be stealthily injected with malware. The malware lies undetected, and while redirecting traffic from a legitimate site to a malicious site, which hosts an exploit kit that can compromise users' machines. Instances of watering hole attacks are increasing rapidly, making them especially important to detect. In this Data Science Central webinar, we'll discuss data science-driven approaches to finding domains that have time and user-based co-occurrence relationships, developed to find low support and high confidence malicious domain associations, and these methods aid in the detection of coordinated network intrusions like watering hole attacks. We'll also demonstrate a scalable and operationalizable framework to detect domain associations by analyzing the web traffic of users in any organization. Anirudh, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Great. Thanks, Bill, for the introduction. So as Bill mentioned, in today's talk, we are going to talk about data science-driven approaches for network security. Specifically, we'll be talking about user and time-based co-occurrence relationships to identify a specific type of attack called watering hole attack. So what exactly is a watering hole attack? As you can see from the figure in the slide, say a user visits a watering hole domain A. So the domain automatically redirects the user to another domain B. Domain B is typically a rare website. So visiting domain B is a low frequency event. But domain B has an exploit kit, and which ultimately leads to the user machine being compromised. So what are the characteristics of this kind of an attack, right? B is relatively unknown, so visiting B is a low frequency event. But B is almost always redirected from A. That is, the conditional probability or the confidence of an initial visit to A, given that B is visited later on, is very high. So these are some of the characteristics of watering hole attacks. So in this talk, we are going to talk about how to detect this kind of attacks by analyzing the clickstream data of users. The goal of this talk is to find the domains that have time and user-based relationships to aid the detection of such coordinated attacks. We also delve a little bit into botnet kind of attacks as well. So the typical steps in any data science process are data gathering, data analyzing, feature generation, model building, and then model validation. So the first step as we delve into the model is to collect the data. For this particular problem, the data sources are the historical proxy logs. Typically, every organization collects proxy logs, which contain information about who is accessing what website and at what time. So these proxy logs are very common across any organization, and as you can imagine, if there are thousands of people in any organization, then the volume of the data that's being collected would be huge. So to give an idea of how the data looks like, for approximately 3 months of data, we would have like billions of connection records. Another data source that we use for this problem is the local domain whitelist. That is the list of non-malicious websites. For example, if we have a list of domains like Google, Facebook, Twitter, etc., these are all non-malicious. So if we can get a concise list of all these domains, that can be used as a domain whitelist. So once we are done with the data gathering, the next step is to do some data pre-processing. So in the slide, it outlines the various steps involved for the data pre-processing. So we'll go into detail into each step. The first step is hostname normalization. So for this kind of attack, we are more interested in the domains that people are visiting. For example, if I visit facebook.com, then my domain URL would look something like anirudh.facebook.com. Similarly, if there's some other user in the organization and he's visiting Facebook, then his URL would look like userb.facebook.com or what have you. So for this particular problem, since we are interested in only the domains and not really interested in the user-specific details of the domain, we do a second-level domain filtering. That is, we pre-process, we normalize this anirudh.facebook.com to something like facebook.com. Then once we do the hostname normalization, the next step is to filter out invalid host names. In any typical data gathering process, we would have a lot of data gathering errors, right? Similarly is the case with clickstream data or proxy logs. So there could be some errors like the website is contains characteristics which are not valid. For example, facebook.com could be something like facebook, com. So this is an invalid host name. So we filter out these invalid host names. Then we identify the unpopular domains. So how we define unpopular is by just aggregating the number of users per domain. If we set a specific threshold and say that the domain is being accessed by a set of users, say less than 50 users, then such domains can be considered unpopular. Say, for example, something like a francelegal.com, that is a website that's not being accessed by most people in an organization, right? So that could be an unpopular domain. So using grouping methods in SQL, we group the domains by the user count and then identify the unpopular domains. So once we do all these pre-processing steps, including hostname normalization, filtering invalid host names, and identifying unpopular domains, the next step is to do a user-specific sessionization, which I'll go into the detail in the next slide. So for each user's proxy logs, we basically sessionize the proxy logs into 2 consecutive sessions if the domain in the two sessions is being separated by a user-defined time window. For example, 60 seconds. So what it means is that for the table on the bottom, assuming that these are the proxy logs for a given user, and you have the connection time and the domain, if you scroll to the bottom and look at the connection time at 12:41:28, the user visits YouTube. But later, after approximately 10 to 15 minutes, he visits something called Facebook. So there is a period of inactivity between his consecutive clickstream visits. So using this information, we basically sessionize the clickstream or the proxy logs into different sessions by taking into account the time at which the domain visit happens. So in this specific example, we take 60 seconds as a time window, but this is very highly tunable based on the application that you're looking at. So once we sessionize this data, the next step is to do the modeling, like extracting patterns from this data in order to achieve the common goal, that is to detect water holes. So before I move on to the modeling approaches, I would like to point out that these kind of pre-processing techniques can be applied to clickstream data in general, not only for security applications, right? Clickstream data arise in various applications like retail, finance, or healthcare, or what have you. So we can use this kind of approach to any kind of clickstream data. But the modeling approaches that we'll talk into in the next slides are very specific to watering hole attacks. So in order to tackle this problem, we use two different modeling approaches. One is called a sequential pattern mining technique, and the other one is a graph mining technique. So the sequential pattern mining technique is a popularly used technique to find time-ordered co-occurrence relationships between a set of items. So in this case, the set of items would be the domains visited by the user. So in order to detect the watering hole attacks, we need to output low-frequency, high-confidence sequence of domains. Similarly, graph mining technique is another popularly used technique where we build a graph or a social network between the domains. The edges between the domains are created by taking into consideration the confidence between the visits of the successive domains. That is, if two pairs of domains are associated with very high confidence, then we connect them by an edge. Once we build the social network graph for these domains, we use graph-based algorithms to find fully and partially connected subgraphs in these social network graphs. So these kind of partially connected subgraphs can lead to botnet-like attacks or water hole attacks. So these two approaches can either be used in conjunction to complement to each other. As for any kind of modeling technique, the main things that we have to consider is the design. In this case, the two design considerations that we take into account are the operational feasibility and the computational tractability. So is our model operationally feasible? To answer this question, given a new amount of data, say weekly data or monthly data, the model should be able to process this new data very fast, and the results that are obtained from the new data should be able to be merged with the data obtained from results obtained from the old data. So our model, the results from our model can be updated to incorporate the results from the old data. So hence, this is a very operationally feasible model. And also, in order to account for the computational tractability, all the algorithms for this model have been implemented using plain SQL and using design-efficient window functions to achieve better runtime performance. So we use the Pivotal's massively parallel programming architecture, that is the Greenplum database, and also use the MADLib functions. MADLib is an in-database machine learning algorithm toolkit for Pivotal. So apart from that, we also use PLR parallelization. So PLR is a programmable extension to R. For those of you who have used R on a single node, PLR enables you to distribute the same code across data that is residing over multiple segments on a Greenplum database. So that way we can achieve better runtime performance and also work with big data in a computationally efficient time. So in this slide, we just show you how the model works, given for an initial run and whenever there's an update, that is whenever you have new data. So on the top, you can see the initial run. Like as I mentioned previously, first is you have an initial proxy logs in the domain whitelist. And once you have that, we do the preprocessing, which is hostname normalization, data filtering, and sessionization. And once that is done, you get a set of preprocessed proxy logs. On the preprocessed proxy logs, we can develop our models, either the sequential pattern mining or the graph-based algorithms, and we get a model-specific results. So given a new data, either it could be weekly data or monthly data, there's an update step. That is, we again get this new proxy logs and updated domain whitelist, and we do the same preprocessing techniques, that is hostname normalization, data filtering, and sessionization. And when we get the new preprocessed logs, we do a model update, that is apply the same algorithm, sequential pattern mining and graph mining. And when you get the model results for the new data, we can merge them back with the results from the old data and update the results based on the previous results. Hence, this is the incremental modeling framework approach. The advantage of this approach is that given a new data, like a new month of data, we don't have to rerun the model for the whole old data and the new data together. Instead, you can just run the model on the new data and then update the results based on the new results. So let's go into the detail of the modeling approaches. The first approach, as I mentioned, was the sequential pattern mining technique. This slide shows you the various steps involved in the sequential pattern mining approach. The first step is we create time-ordered domain sequences from the sessionized data. Once we have these domain sequences, then given a list of targeted domains, that is, they could be rare domains, or if you have a known blacklist, that's also fine. We select subset of sequences containing those domains. Once we have the subset, we find high confidence and the low support sequential patterns of targeted domains in parallel for all the subsets of the domains. So this is an overview of the modeling approach for the sequential pattern mining. So let's go into the details, right? The first step in sequential pattern mining is to create sequences. So each sequence contains domains in a session for a particular user. For example, on the right-hand side, we have the connection records for a particular user. Once we sessionize those records, we can convert those sessions into sequences by grouping the sequences for a particular user belonging to a particular session, right? One thing that has to be taken into account is that the domains in a sequence are ordered by the connection time. So there are time-ordered domains within a sequence. Also, in some cases, it might happen that some domains within a sequence might be repeating. Say, for example, there's a clickbot which goes to a particular website and clicks it every second. So that domain might be repeating every second within a sequence. In that cases, we take the minimum time for that sequence. So every sequence contains a unique domain. There's no repeating domain within a sequence. So for the example on the right, as you can see that if there are the sessions from a single user, then there are two sequences. The first sequence corresponds to the first session, which contains domains like Google Video, Twitter, YouTube, DoubleClick, Google, and Google Analytics. The second sequence contains Facebook and Yahoo. So this is how we convert the sessions into sequence, by taking into account the time order between the domains, and also make sure that there are no repeating domains within a sequence. So for any model, the first step is to generate the features. In this slide, we're going to talk about what are the features that are required for this modeling approach, right? Some of the statistics that we use for the sequences. So the table shows 10 sequences from a single user. The first column shows the ID of the sequence, and the second column shows the items in the sequence. In this case, the items are the domains visited by the user and their time order. For example, the sequence ID 1 says that the domain A is visited before domain B is visited before domain C, right? So we have a set of 10 sequences. Support of a pattern is the ratio of the sequences in which a particular pattern appears. For example, if we are looking at the support of a pattern AE, we can see that AE appears in the sequence ID 4 as well as sequence ID 7. So out of the 10 sequences, the pattern AE appears in 2 out of the 10 sequences. Hence, the support of the pattern AE would be 2 by 10. The confidence of a rule X implies Y is the proportion of the transactions containing X that also contain Y. So for example, if we want to find the confidence of a rule A implies E, we have to find out the patterns, the sequences that contain both A and E, and also the sequences that contain only E, and then divide them. So in terms of support, the confidence can be written as support of AE by support of A. So in the table on the left-hand side, you can see that the pattern AE appears in 2 out of 10 sequences. And if you want to count the number of sequences in which pattern A appears, it appears in sequence ID 1, sequence ID 2, sequence ID 4, 5, 7, 8, and 10. So it appears in 7 out of 10 sequences. Hence, the confidence of the rule X implies Y would be 2 out of 7. Another feature that we use for building this algorithm is the number of users. Say the number of users is the number of distinct users for which a particular pattern P occurs. So assuming that the table is from a single user, so the number of users for any pattern, say pattern A, would be 1. So these are some of the sequence statistics that we use for building or developing the algorithm, right? One other important thing that I want to point out is that in order to make the algorithm efficient, we make use of some facts about these statistics or the features. Support and the number of users follow a monotone property. So what exactly is a monotone property? If X is less than Y, then any function of X would also be less than any function of Y. So how does it apply to support and number of users? Say, consider a pattern AE. We know that AE is a subset of A. Now, since support follows the monotone property, we can say that the support of AE is always less than support of A. As you can see for this example, support of AE was 2, but support of A was 7. Hence, it satisfies the inequality. So that can be verified for any pattern that is a subset of any other pattern, right? Similarly, the number of users also follows the monotone property. That is, number of users of a pattern AE would be less than number of users of A, since AE is a subset of A. So in this slide, we have talked about some of the features and some of the properties of those features. So we make use of those properties and we develop an algorithm in our Greenplum database, which is highly scalable. The sequential pattern mining algorithm is based on the principle that we first consider single item domains, that is single domains visited by a user. And then we calculate the support and the number of users for those domains. If we find some domains whose support is less than a particular threshold, we prune those domains. Then we go to the second pair of domains, that is 2 item domains, say A, B, B, C, and stuff like that. Using the property of that support and number of users follow monotone property, we can say that only the 2 item domains that are occurring from the frequent 1 item domains would be frequent. Hence, the support and number of users would be very useful to prune these higher level domains based on the lower level domains. So once we have those domains satisfying a given support and the number of users condition, we find out among those patterns of domains which are the patterns which have very high confidence in order to identify the watering hole attacks, right? So the graphic in the slide shows how the parallelization takes place. First, we identify domains with small support, or known bad domains. Say it could be a known blacklist of domains. So once we have this domain A with a small support, we subset all the sequences from the data containing the domain A. Once we have the subset of sequences, then we apply the sequential pattern mining algorithm on the subset to find the high confidence patterns from these domains. So the beauty of the MPP architecture is that each domain can be, the data corresponding to each domain can be distributed across a different GPDB segment node. And hence all the computations, the algorithms can be executed in parallel instead of happening sequentially. That way it is much faster and it is very highly scalable. So the high confidence patterns relating to a given set of domains are obtained in parallel in this way. That is, the sequential pattern mining algorithm runs independently on different set of sequences for different domains. So the pseudocode for this is is shown in the slide. It's a simple SQL-like function where you say select a targeted domain and apply the function sequential pattern mining algorithm with the necessary parameters. In this case, it could be the minimum support, the minimum confidence, and the minimum number of users from the input table. So that's how the pseudocode for this looks like. So as mentioned in the previous slide, for each domain of interest, the sequential pattern mining algorithm is run on only a subset of sequences containing that domain. So as a result of this, this may lead to some sequential patterns having very artificially high confidence. So recall that the confidence of a pattern X given Y is nothing but the support of X, Y and divided by the support of X, right? So support of X is nothing but the number of sequences in the subset that contain the left-hand side pattern, that is X. So this may not reflect the popularity of X in the full data set, since we are only taking a subset of the data. So in order to avoid that, we define something called relative confidence. And relative confidence of a pattern X implies Y is nothing but support of X, Y by support of X in the full data set. So relative confidence basically favors patterns whose left-hand side, that is X, contains less popular domains. For example, in the slide, you can see two highlighted relative confidence values, right? Say for a particular domain, as an example, revenueindia.net, we are looking at two patterns. One is google.com, facebook.com, and revenueindia.net. Another one at the bottom is fileshare.com, redworm.com, and revenueindia.net. As you can see in the confidence column, both the patterns have relatively high confidence. That's 0.75 and 1, which is greater than, say, a threshold of 0.5, right? But when we look into the relative confidence, we can see that Google and Facebook are very popular domains. It could so happen that the subset we chose, the support of these domains would be really low. But when we take the whole subset, the relative confidence would decrease a lot because the support of those domains would be high. On the other hand, FileShare and RedWorm are relatively unpopular domains. Hence, the support in the full data set wouldn't be much compared to the support in the subset. Hence, the relative confidence is still comparatively high comparing to the former, right? So you can see that the relative confidence favors unpopular left-hand side patterns. So the main reason for doing this is to order the domains based on relative confidence. That is, the domains or the patterns with very high relative confidence will surf up at the top, and then we can filter out those patterns which have less relative confidence. So these patterns with high relative confidence would be probable watering hole attacks compared to the others. So the model update step for this sequential pattern mining approach is a simple update of the sequential patterns. That is, we simply merge the new results obtained from the new data with the existing set of patterns. That implies updating the rule quality metrics like support and confidence. So as you can see, there's just one more step where we merge new results with the existing set of patterns. So that kind of gives an overview of the first approach, where we use sequential pattern mining algorithm to find out patterns of domains that are highly correlated to each other based on high confidence values, and also have low support and a specified number of users accessing those kind of patterns. So the next approach that we talk about is another popular approach called a graph mining technique. So the graph mining is applied across various domains like security, healthcare, and also social network analysis. So the various steps involved in this graph mining technique are as follows. First is we construct baskets of domains. These are nothing but co-occurring domains by running a sliding window of certain interval through the data. Once we construct these baskets, then we try to find out high confidence, low support, pairwise association rules of the form domain 1 implies domain 2. So once we, the main difference between sequential pattern mining and the previous approach and this association rule mining is that here we mostly concentrate on pairwise associations. The reason for that is that once we have those associations, we create a social network of those domains, which will become clear once I talk more in detail. Then from the social network, we find partially and fully connected subgraphs. So the first step, as I outlined previously, is to construct baskets of domains. So domains visited by a user in a certain time window would form a basket. This is similar to items purchased in a single transaction whenever a person goes to a shop and buys something. So on the right hand side, you can see again some domains visited by a particular user. So the baskets would be created by taking, say, 60-second time window. The first domain is visited at 1441. Similarly, the last domain in the first basket would be visited at 1442. So all the domains visited in a 60-second window would be falling in a basket. So this parameter, the time interval for creating the baskets, is highly tunable. In this case, we use 60 seconds, but based on the application or based on the problem that we are tackling, that can be varied. So one other thing to note is that a basket contains distinct domains, and a sliding window is used to create multiple baskets. So example on the right, the first basket would have something like Google, Twitter, YouTube, DoubleClick, and Google. So these domains in the basket are again time ordered and they are distinct. That's something that we have to take into consideration. So what we have done so far is mapped the given data into a set of baskets, where a basket contains a set of domains. So once we have converted this data from a table format to the basket assignments, the next step is to find the pairwise association rules among these domains. So the first statistic is to find out the co-occurrence frequency. That is the number of times two domains fall in a common basket. That will give you the count of how many times these two domains co-occur with each other. The other thing that is of concern is the conditional probability. That is the probability of seeing domain 2 given domain 1 is present. That is, if you have a basket which contains domain 2, what is the probability that the domain 1 is also present in that basket? So we developed this kind of basket creation as well as association, rule mining, and statistics generation in a plain SQL in a scalable fashion on a Greenplum database using window functions. So on the bottom, we can see an example of how a result of association rule mining looks like. So the first column is a domain A, that is the first domain, and the second column is a domain B, that is the second domain. So the third column gives the number of baskets in which A and B co-occur. So in the table, if you see a highlighted domain, the pivotal and science fiction, they co-occur in 78 baskets. The fourth column gives you the number of baskets in which pivotal alone occurs. So it might be a popular website that most people access, so it occurs in 560 baskets. while science fiction occurs in a relatively lesser number of baskets, that's 97. The sixth column gives the probability of A given B using Bayes' theorem that's calculated by probability of A intersection B by probability of B. That is nothing but number of instances in which A and B co-occur, that is 78, by the number of baskets in which only B appears, that is 97. So dividing 78 by 97, we get 0.8. Similarly, you can find out probability of B given A using Bayes' theorem. Also, we can calculate the user column, which says the number of users in which these two domains occur. In the example, it is 4 users have these two domains co-occurring with each other. And also, the other column shows you the maximum and the minimum date in which this kind of pattern appears. So typically, high confidence, that is greater than 0.5, associations involving multiple users over several days. For example, the highlighted rule, which has a high confidence of 0.8 and it appears in at least 8 days and at least 4 users, they're generally more interesting. Because watering hole attacks are targeted to domains that are at least accessed by a couple of users. And also, they generally span for at least more than a single day. That's why we concentrate on these associations for which have high confidence and across several days. So the reason for finding the pairwise association is to build a graph. Once we have these results from the association rule mining, we build an undirected correlation graph. So the figure on the right shows you an example of a graph where each node denotes a domain and each edge denotes the confidence between those domains. So we can choose a specified confidence, say 0.2 or 0.5, and then build this graph. So that is, if two domains have a confidence greater than a threshold, then only we create an edge between those domains. So for all the domains in your network, first thing is we build this huge graph and create all the edges between any pair of domains. So for example, the example on the right shows the tightly connected social network for a particular domain. So once we have the social network, the next thing we do is to find out clusters in this graph, that is partially and fully connected subgraphs that could possibly indicate waterholes or botnet attacks. It could indicate waterholes because we are looking at domains that have very high confidence in association and the support is very low. That's what is the main criteria for finding waterholes. So the question arises is how to quantify these kind of networks and how to find the subgraphs, right? So we use a commonly used method called an oddball approach to quantify the connectivity of each domain's network. In order to find the oddball metric for a domain, we identify each domain's one-step neighborhood. This is also called the egonet. That means the first neighbors for each domain. Once we have the egonet, we extract two graph features from the egonet. One is n, that is the number of neighbors, and e, the number of edges in the egonet. The number of neighbors and the edges follow a power law. That is, edges are proportional to n power alpha, where alpha generally lies between 1 and 2. The figure below shows the plot for log e versus log n. So log e versus log n is a linear plot where the slope would correspond to the value of alpha. So if the slope is 1, that means the number of edges are equal to the number of neighbors. So that would be a graph as shown in the figure where the center node is connected to all other external nodes. That is an example of a telemarketer or a spammer who is targeting a couple of users and then the users don't talk among each other. If the slope is 2, as shown in the figure, that would be a perfectly connected graph. This is an example of a discussion group where everyone is talking to each other. Typically, the oddball metric, which is the slope, if it is greater than 1.5, that is more interesting because that would indicate that there is some amount of connectivity in the graph. We also look into another metric called the click percentage. That is the ratio between the number of edges in the EgoNet to the number of edges needed to form a click. A click is a fully connected graph. So if there are n nodes in a graph, a click would have n square plus n by 2 edges. So the click percentage is nothing but E by n square plus n by 2. So this click percentage is also used to measure the network connectivity. So the sample results from this approach are shown in the figure. So on the figure bottom, for a particular domain of interest, we first find out its EgoNet, that is the first nearest neighbors. So in this case, it could be something like B, C, D, and E. As you can see, A is highly connected with B, C, D, and E, which are also interconnected with each other. Hence, that is a perfect click. So the click percentage for this particular EgoNet would be 100%, as shown in the highlighted row in the table. Also, if you see the oddball metric, that is nothing but log E by log N, that would be 1.66. And there's another column which says the number of users that are accessing this central domain. So for each domain, we can calculate these statistics, that is the number of edges, the oddball metric, and the click percentage. And once we have this, we rank these domains based on these click percentages. That means the domains which are having very highly connected networks are possible waterhole domains. That means if we know a particular domain in that network that is malicious, then all other domains in the EgoNet, in the tightly connected EgoNet, would also be something that could be malicious. So these EgoNets would help the forensic expert to look into other domains in the EgoNet that are also malicious, given known malicious domains. The other technique that we use from this social network graph is that to identify isolated groups of domains that only interact with domains in the same group and do not interact with anyone else. So this is exactly a botnet-like structure where the domains are interacting with only the domains in its group while they don't interact with anyone else in the whole community. So this can be formulated by finding the connected components in the graph. Connected component is a popularly used graph mining technique where we are trying to find out isolated clusters or isolated subgraphs in the graph which are only connected to the other elements in the graph but not to the entire population. So for example, in the bottom you can see a sample connected component. You can see that all the domains are just connected to other domains in this connected component, and this connected component would be isolated from the rest of the big graph formed from the social network of the domains. So if we know that the central domain, that is BCD, highlighted in orange, is malicious, we can also see the other domains that it is connected to and attribute the risk to those domains given a known domain in the network. So these are the two models that we have used to address this particular problem. One is the sequential pattern mining and the graph algorithms. So let's look into how to operationalize this model when we are running it across an industry setting. So the first step is to load data. That is typically owned by a data engineer where he loads new data. And the next step is to run algorithms over that data. That is typically first done by a data scientist where we develop the algorithms, and once we have a cron job which can be done just by clicking the button, that can be owned by a data engineer who runs this model on a weekly or a monthly basis. So once we have this model, the next step is to inspect the anomalies from the model. The model flags some suspicious domains, for example, which could be possible waterholes. Then the security experts in the organization can look into those anomalies and then provide more feedback to the model. So ideally, the model outputs would be provided via interactive dashboards. We also have an app development wing at Pivotal, the Pivotal Labs, which actually develops mobile apps for organizations. Once we have these anomalies, we can use those feedback from the security analyst to improve the model. So this typically is owned by a data scientist who refines the algorithms based on the output and the feedback from the security experts in the organization. So the whole cycle repeats every week. So whenever you have week or a month, whenever we have new set of data, then that can be loaded, and then we can run the model. And as I have mentioned previously, it's very operationally feasible. That means given a new set of data, we don't have to use the old data and rerun the results across the combined data, but just get the results on the new data set and then update the patterns based on the old results. Right? So this is the operationalization vision. If this model has to be applied across a huge organization, and then every week or every month, this model outputs a set of domains which are flagged malicious, and the security experts can look into those domains and then make decisions and then further improve the model. Yep. So I guess that concludes my talk. We can leave the rest of the time for the Q&A.
Okay. Anirudh, well, thank you so much for that excellent presentation. So as you suggested, let's get started with today's Q&A session. And I want to thank the audience for their participation. We have a great many questions that have come in during the presentation, and we'll do our best to get through all of them in the time remaining. So during this Q&A session, I'll leave this screen up, which gives Anirudh's contact information in case you'd like to get in touch with him after the presentation. So let's get started. Anirudh, this watering hole with redirect model, is that a common malware strategy, or is it more rare? Is this something that companies should be looking for, or just one of many types of malware attack?
Oh yes, waterhole attack is a very commonly occurring attack, and many high-profile companies have also been compromised by this kind of attack. So everyone should be looking out for these kind of attacks. And as I mentioned previously, these attacks are targeted towards a very genuine-looking website. So if we have a rule-based approach where a company basically puts a blacklist of websites that are known to be bad, that method wouldn't work to detect these kind of attacks. Even genuine websites can be compromised by these attacks. So it's very important that we have every company should be looking out for these kind of attacks, and increasingly data science and machine learning can develop models for tackling these kind of attacks.
Well, and your presentation was very comprehensive. Is this approach something that Pivotal offers as a service or a package?
So at Pivotal, this is typically offered as a service, but it can be offered as a product as well. So the way the Pivotal works is that we are a team of 40 data scientists spread across the globe, and we have typical engagements like 6 weeks to 12 weeks. So given a new problem or any organization has, say, waterhole attack detection, or any other new problem or new model that a company wants to address, then we engage our data scientists for 6 weeks or a 12-week engagement and develop an end-to-end model that the organization can later use when we are away, and it can. So the organization should be able to run the model by themselves. So that way we offer a service for 6 weeks or 12 weeks.
Good to know. Good to know. So we know where to go to get help. You know, to come back to some of the more technical issues of your presentation, would you speak to the issue of the computational complexity of the sequential pattern mining algorithm? And we have one audience member who has asked, what happens when the sequence gets too long? What do you suggest? In this case, he's talking about a sequence that is 400,000 items long.
Yeah, so the computational complexity is based on the number of items in the particular sequence, right? So if you are looking at an M item sequence and we are looking at a pattern consisting of K domains, then the computational complexity would be of the order M par K. So to address the question, if we are looking at very long sequences, so there could be a parameter that could be tuned in the model where we can limit the number of sequences that we are, length of the sequences that we are looking at. So typically for the waterhole attacks, as I mentioned, the pattern that we are targeting would be at least minimum 3 or 4, because the way the attack occurs. So whenever a genuine person goes to a website, he's redirected to another website. So that's like a two-length pattern. So we can tune the patterns based on the length of the pattern in the algorithm.
Excellent. Excellent. Thank you. You know, there's a question here that relates very much to an interest of mine. When you talk about operationalizing this system, you've talked about a cycle of a week. So my question is in two parts. Is it possible to get this down closer to real time or even in stream? And of course, recognizing that you've got a human element with the security analysts stepping in to look at your suspicious sites, what's your success rate? What sort of false positive rate are you finding from your procedure?
Yeah. So if I understand the question correctly, there are two parts of the question. First thing is, what is the role of the security analyst, and how can the knowledge gain be used in the model, right? So,
well, and how can we shorten the cycle down toward real time?
Yeah, how can we make it more real time? So, first thing is the model learns from the historical data, right? We need to have some historical data to be able to know what patterns are occurring in the data. Once you run the model on historical data and you have a set of rules or set of patterns that the model outputs, then that could be added to the dictionary, like to the rule set or the dictionary, and then whenever we see that kind of pattern appearing in real time, that can be flagged. So that's how we can use it in real time, by learning from the model, getting more patterns from the data, and then using that for real time. So the other question is with respect to the false positives. So that's where the security expert would come into play, and then he can give us an initial input to the model where we are specifically targeting to a list of domains, right, when we are running the model. So that list can be provided by the security experts. So that's where the false alarm rate can be decreased.
Right, right. Okay. I'm sure we would all like to get these sites on the blacklist as quickly as possible. But the needle in the haystack problem is one that's very difficult for data science. I appreciate that. Would you speak to the issue of to what parameters are supplied to the sequential pattern mining algorithm?
Yeah. So as I mentioned previously, some of the parameters that I supplied are the minimum support, that is the number of sequences in which the pattern is supposed to appear, and the confidence. So since we are looking at high confidence patterns, typically we probably want to put the confidence to around 0.8. And the other thing is the number of users. We are looking at patterns that appear in a minimum of say 3 or 4 users, right? So that's one of the patterns. And also the other thing that can be tuned, as I mentioned, was the length of the pattern. That means we can say what length of the patterns are we looking to output. So we can say we are looking at only 3 length patterns or 4 length patterns or what have you. So these are some of the parameters that can be tuned in the model, and also the window size that can be tuned. So for generating the sequences, in our example we use 60 seconds, but that can be tuned based on the application. So you can either make it 1 minute or more than that.
Okay. Okay. Some other technical questions that have come in from the audience. One asks, why didn't you use Apache Spark in place of the PLR routines? Any specific reasons?
Yeah. So this model was developed on the Pivotal stack. So we use PLR as the beauty of PLR is that it can be used on Greenplum explicitly once the data was residing on the Greenplum. So for this example, the data was residing on the Greenplum, so we used PLR in that case. But if we had the data that could be accessed by Spark, then definitely Spark could be used as well.
Okay, then perhaps this question relates to the same thing, because an audience member is wondering why you custom developed the CLR function in SQL instead of utilizing something like Microsoft's pre-existing association editing in SSAS. Yeah,
so typically all the algorithms that are available over there take into account only the minimum value of the support. For this particular example, we want to include more parameters. For example, the number of users. The algorithm is customized for this application because we also want to look at the number of users. As I mentioned previously, while developing the algorithm at each step, we use the monotone property to prune the rules based on both the support and the number of users. All the algorithms out there typically only allow you to specify the support, but it doesn't allow you to specify the number of users as an extra parameter. So we developed this algorithm in our database. And also, we saw that the database-specific functions are much faster, like window functions and anything implemented in the database is much faster than if you're using R or PLR.
Interesting. Now, graph mining can be a particular knotty problem for a lot of data scientists. How do you get around the problem that graph matching is an NP hard problem?
Yes, that's a very interesting question. So we have developed a lot of algorithms, like patent pending algorithms in Pivotal, like the connected component algorithm. We have tested it across our big graphs, and it runs especially fast. So the way the algorithm is developed takes into account that it's computationally very feasible. And for this particular example, since we are looking at egonets of specific domains, so the graphs, even though the whole graph might be big, but the egonet would be only relating to the first neighbors. So it wouldn't be that computationally expensive compared to analyzing the whole graph. But that's a good question, and that is something a lot of research is going on within our team to address all these graph mining algorithms and the computational complexity with respect to them.
Yeah, I think the audience must appreciate that we're hearing about very cutting-edge procedures for this type of malware detection. So let me ask a combined question. First of all, what other domains can this approach in pattern matching be used? And the second part is, are there commercial packages that already utilize this procedure?
Yeah, so talking about the domains where this can be applied, so this procedure can be applied across any area where there are sequences. Say, for example, healthcare, where you have gene sequences, and we are trying to find patterns in those gene sequences. That is one example. And also, if you have the retail and clickstream data, where we are trying to find out if a particular user buys a particular product, what else are the other products that the user can buy. So in that case, also this sequential pattern mining can be applied. And security as such is generally a whole huge domain where we always are looking for patterns and needle in haystack kind of anomalies. So this technique is widely used in security. So that answers your first part of the question.
Right.
Can you? So about the commercial.
Yes.
Yeah, about the packages out there. So there are packages out there in R and Python which implement the sequential pattern mining algorithm and association rule mining algorithm. So that can be used, but there are serious limitations on the computational complexity and the speed, and also the parameters that you can input to the algorithm. So for example, this was a custom built solution. In order to be able to input the number of users as an extra parameter. So there are actually algorithms or the packages out there implementing these algorithms, but depending on the specific application, there is a lot to be tuned for those custom packages, and they can be directly applied to your solution in hand. And especially in security, the threats are evolving with time. So each threat is very different. There's no signature for this threat. So every problem or every attack should be handled separately, and we need a different model for each attack.
Well, Anirudh, thank you so much. Some great answers to some very good questions. And for those of you that have asked questions today that weren't answered, we'll be sending all the unanswered questions to Anirudh and the Pivotal team so they can follow up with you after today's webinar. I have just a few quick announcements. Please mark your calendars for October 27th. That's our next DSC webinar, Enterprise Predictive Analytics, Success Stories, and that's going to be sponsored by Alteryx. Also, remember, today's taping will be available for on-demand viewing later today and can be found on the homepage of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks again to Pivotal for their sponsorship and our speaker today, Anirudh Kondaveeti, for his insight into today's topic. My name is Bill Vorhies, and I'm very pleased to have been your host for today's event. I look forward to seeing you all again on October 27th. Have a great day.